Okay, in this video, we're going to revisit a topic that you have covered in Calculus 1 on tangent line approximations. So if a function happens to be differentiable, then at that point, you could draw a tangent line to that function. And if you zoom in, the tangent line and the function itself are very close to each other, as long as you don't stray too far away from where it's tangent to. So we're going to revisit that, and then we actually have more tools now. So we're in a better position to say more things about it. So let's get right to it. Okay. So let's do a warm-up problem. So it's been a while since you've done Calculus 1. So let's talk about how to find linear approximations of a function. Let's first look at the function e to the x. So I have to find the derivative, but that's easy because derivative of e to the x is e to the x. And I want to know, I want a tangent at x equals to 0. So to do that, I'm going to have to look at the function value at 0. So if I plug in e to the 0, e to the 0 is 1. And the slope there at the point where it's tangent is also 1. Okay, so I have e to the x here. Okay, and then I'm looking at x. This height is at 1, and the slope of the tangent line is also 1. Okay, so I'm going to use this formula for line. So if I pass through the point x naught, y naught, and the slope is m, then the equation of a line is given by that. So my tangent line has slope 1, x minus x coordinate where it's tangent to is 0, plus the y value is 1. So I guess x plus 1. So it got a little cramped there. So that's a tangent line at 0. Let's do natural log of x, tangent at x equals to 1. So again, taking the derivative. So derivative of natural log is 1 over x. I plug in 1 into the original function and the derivative. So g of 1 is natural log of 1, which is 0. And g prime of 1 is 1 over 1 over x, and x is 1. And so the slope is 1. So using the same formula, y is equal to, the slope is 1, x minus 1, plus the y coordinate at that point is 0. So we just have x minus 1. I'm going to call this t of x. Okay. All right. So if the process made sense to you, I want you to try doing the tangent line of sine at x equals to 0 as well. But let's move on. So in general, linear approximation, or also called first Taylor polynomial, and line is a polynomial, right? Technically, and if you want a tangent at x equals to b, this is the formula we could use to get that. So I kind of swap things around. So this is the y coordinate at the point where I want it to be tangent at. So that's my f of b, and plus the derivative at that point b, f prime of b, and then multiplied by x minus the point where it's tangent at, the x coordinate where it's tangent at. Okay. So I'm going to call this T. In fact, I might call it T1 for first order Taylor polynomial. T is for Taylor, not tangent. Okay. All right. So we've done this. I don't know if you remember or not, but we've done this in Calculus 1. And that's a topic there. But the thing about approximation is that it is kind of useless, or it's not as useful if you don't know how much you're off by. So in Calculus 1, we just said, we plugged in some numbers and say, hey, it's kind of close. But now we could actually work out what the error would have to be. So that's what I want to do next. So I want to compute what's the error, or at least approximate the error, so that like we can be confident that we're this within certain precision from the answer we're looking for. Okay, so what tool do we have now that we didn't in Calc 1 is one of the tools is integrals. So let's use that. So I'm using the fundamental theorem of calculus part, I think it's part 2, which we use all the time to compute antiderivatives. So we know that the area underneath f prime from b to x is the same thing as the difference for the upper and lower limits of the antiderivative of f prime, which is the original function f. So this is the fundamental theorem of calculus right here. And then while computing this integral, we're going to do something slightly different. We're going to do integration by parts and see what we get. Okay, so this is my u, f prime, and this is my dv. So I'm using integration by parts. If you have integral of u dv, that's the same thing as u times v minus integral of v du. So this is what I'm using. If u is f prime, then du is the derivative of that. So f double prime t dt. And if dv is equal to dt, the antiderivative of constant 1 is going to be t. But actually, I'm going to write it as t minus x. So I'm allowed to do that because x is constant with respect to this this equation. The variable integration is t, and when dv is equal to 1, I could use any antiderivative of constant 1. So antiderivative of 1 is t plus some constant, and I'm choosing that constant to be negative x. Okay, so this will come into play in the formula. So that's why I'm choosing this weird antiderivative. Okay, so now that I have this thing, let's plug that into the formula for integration by parts. So now I have u times v right here. And this is going to be evaluated from t equals b to x minus the integral of v, which is t minus x here, and du, which is f double prime of t dt. Okay. So let's do the outside of the integral first. So I'm going to plug in x first. So if I plug in x into t, I have x minus x here in front of the f prime of x. And x minus x is 0. So when you plug in x, you get 0. And then minus, you can plug in b for the place of t, and I get minus b minus x times f prime of b. All right. Okay. And I'm going to, I have the integral over here from b to x. I'm going to flip the t and x here and make it into x minus t instead of t minus x. That flips the order of subtraction. So I need a negative sign to make up for that. And there's already a negative sign in front of the integral. So I'm going to cancel that and make it into a positive here. Okay. And then what I'm going to do is I'm going to bring this term over to the left-hand side of the equation. So the left-hand side of the equation is f of x minus f of b. And if I bring this guy over, I get f of x minus this guy, f of b plus f prime of b times x minus b. The reason why I'm grouping it this way is because that's it. That's what I have here. This is the tangent line approximation, or the first order Taylor polynomial. Okay. And what I have here on the left is the true error to this approximation. So this is the original function. And if you subtract away the approximation, you get the error. And the error itself is represented by this integral right here. Now, this is a complicated expression involving second derivative and multiplied with something else. So it's not an easy thing to compute, but let's say we have some way of approximating the second derivative. So I'm going to assume some things. I'm going to assume that the second derivative is no bigger than some number big M. Okay. Suppose I have this approximation in this interval from x to b or b to x. See what kind of expression I can get. All right, and I'm also going to look at the absolute value of this error because I might not be able to control if it's an overestimate or underestimate of the true function that I'm looking at. All right, so the first step of the approximation, I'm going to put the absolute value inside of the integral. So let's see. So this might have been inequality that you have seen in Calc 2, but let me review it very briefly. So it turns out that if you bring the absolute value inside, you might get something larger. And the reason is because the function could look something like this, where some parts of it is above the x-axis and some parts is below the x-axis. If I'm looking at an integral like this, when I integrate, the negative parts below the x-axis, the negative area, could cancel out with the positive area. But if you took the absolute value before you take the integral, right, everything is positive. So area that went below the x-axis, which usually counts as negative area when you integrate. But if you flip that to the positive side, all the areas add and none of them will cancel. So if you bring the absolute value inside, you might actually get a larger area. So that's what I'm doing here from this step here. Okay, I just brought the absolute value inside. I don't need the absolute value in front of x minus t because I'm thinking of t as some number between b and x. So this is a positive expression. Okay, now I'm going to use the assumption that f double prime is less than or equal to some constant m. So I'm replacing this with the constant m. And since m is a constant, I'm going to pull that outside of the integral. And now what I have left is antiderivative of x minus t, which is a very reasonable thing we can compute. And then at the end, plugging in x and b, here's what I have left. So m divided by 2 times x minus b squared. And when you square something, it's always positive, but I'm going to put absolute value here for consistency, or the formula we're going to get later. It doesn't matter much if I use absolute value or not. Okay, so this is the tangent line error bound. So as long as you can have some estimate of how big the second derivative could be, then you can control what the error is going to be. So the error is always bounded by that. Whatever the second derivative is bounded by, divided by 2 times x minus b squared. And x minus b is the distance from the where it's tangent at, right? So it's tangent at the value b. So if x minus b is small, then you're close. And small number squared is going to be even smaller, right? So that error is going to be much, much smaller if x is very close to b. And this formula gets at exactly how close it gets. Okay, let's use this formula in practice. So we had a couple examples we had earlier. So we know that function e to the x has a tangent tangent line x plus 1 when it's tangent at 0. And let's see what's the worst case scenario, like how large could the error be if I'm looking at the interval from -1 to 1. Okay, I kind of want to bound the interval I'm looking at because if I look, what's the worst case error? If you make the x very large away from where it's tangent at, then error is going to blow up to infinity. So I want to look at a finite interval from -1 to 1, centered at 0, and see how bad the error could be. All right. So to use this formula, I need to estimate the second derivative. So f prime of x is e to the x, and f double prime is, again, e to the x. And how large could e to the x be in the interval from -1 to 1? Well, it's the largest when x is equal to 1. So f double prime of x is always less than or equal to e to the power of 1, or just e. Okay. So using the formula, error is less than or equal to e divided by 2 times x minus the place where it's tangent at is 0 squared. Okay. So you could say e over 2 times x squared is the worst case scenario. X squared, the largest that is going to get is 1, right? So I might plug in x equals 1. And e divided by 2 is the worst error you can get in that interval. Okay, I hope that made sense. Let's try that again with the function natural log of x. So the tangent line for this guy happened to be x minus 1. And let's see how close this line gets to natural log of x. And let's say we're looking at a very close interval here. So the tangent is at 1, x equals 1. So let's look very closely nearby there. So from 0.98 to 1.02. So you're within 0.02 from where it's tangent. So the error should be small because we're very close to the tangent line, tangent point. Okay, so we take a couple of derivatives. So derivative of natural log of x is 1 over x. And the second derivative is -1 over x squared. And how large could that get in absolute value? Well, let's see. So negative I can ignore because I'm taking the absolute value. And this fraction is largest when the denominator is the smallest. So if I plug in 0.98 to the x here, okay, that is the largest the second derivative is going to get in this interval. Okay, so that's my m. All right, so what is the error? Error is this m, so 1 over 0.98 squared divided by 2 times the x squared. So, sorry, x minus 1 squared. And the largest you could get from 1 is 0.02. Okay. So let me type this into the calculator. Okay. 1/2 times 1 over 0.98 squared times 0.02 squared. Okay, so the worst case error is 0.000208247. Dot, dot, dot. Okay. So the error is going to be less than this in general. So it's less than or equal to. So the worst error you could get is 2 1,000. So 2 10,000ths. So it's a very good approximation in that interval. And e over 2, this wasn't such a good approximation because the interval was not very closely bound where it's tangent at. Okay, but now we're getting concrete numbers, so we know what to expect from our approximation. All right, so if that made sense to you, I encourage you to try the exact same error bound for the function sine of x between negative 1/2 to positive 1/2. So try that out. But I'll end the video here. So I'll see you later.